Look around and you'll notice water pulling off a physical trick no other natural substance on Earth can manage. Depending on the ambient temperature, it exists in three completely different physical forms. In its solid state, as ice, it is rigid. It holds a fixed shape and a fixed volume, meaning you cannot easily compress it or force it to conform to a new space. Warm it up and it becomes liquid water. Now it flows easily, instantly taking the shape of whatever container you pour it into, even though its total volume stays exactly the same. Add enough heat and it turns into an invisible gas called water vapor. In this state, it abandons both fixed shape and fixed volume, expanding rapidly to fill whatever empty space it can find in the air. Whether a hard block of frost, a flowing river, or steam rising from your coffee, you are looking at the exact same substance, just operating under a completely different set of physical rules. To understand why these forms behave so differently, we have to zoom in to the molecular level. This diagram shows how the particles are packed in each state. On the left, the molecules in a solid are locked into a tight, vibrating grid, preventing them from flowing. In the middle, the liquid molecules are clustered, but loose enough to slide past each other. And on the right, the gas molecules are scattered, bouncing around at high speeds with total freedom. But there is a strange anomaly hidden in how water handles this transition. Almost every substance in the universe packs its molecules tighter together when it freezes. Water does the exact opposite. As water freezes, its molecules arrange themselves into a rigid crystal structure that actually leaves more empty space between them. Because the molecules are spread further apart, solid ice is less dense than liquid water. Because it is less dense, ice floats. When winter hits, lakes and oceans freeze from the top down, creating an insulating shield on the surface. This prevents the entire body of water from freezing solid, allowing fish and aquatic plants to survive the freezing months below. What actually forces water to jump between these states is heat energy. Adding heat feeds the molecules energy. They speed up, eventually breaking the bonds holding them together to melt or boil. Removing heat forces them to slow down, allowing those bonds to lock them back into place to condense or freeze. This chart tracks the temperature of water over time as we heat it. If we continuously apply a flame to water that is already boiling, you might expect the temperature line to just keep going up. Instead, the line completely flatlines at 100 degrees Celsius. This plateau represents a concept called latent heat. Latent heat is the thermal energy required to change the state of a substance without changing its temperature. During this flat period, the flame is still burning, but the heat energy is no longer making the water hotter. Every ounce of that energy is being consumed to break the molecular bonds and force the liquid to become a gas. Changing states requires a massive transfer of hidden energy to physically restructure the molecules, keeping the temperature perfectly stable until the job is done. This brings us to a common point of confusion. There are actually two distinct ways liquid water turns into a gas: evaporation and boiling. Boiling is a rapid, violent process that only happens when you force the entire volume of water to reach 100 degrees. Evaporation is a quiet process that happens entirely on the surface of the liquid, and it occurs continuously at almost any temperature, even on a cool day. If you want to speed evaporation up, you can raise the temperature, increase the wind speed to blow the saturated air away, or spread the water out to expose a larger surface area to the atmosphere. On the cooling side of things, you will often hear the terms freezing and solidification used interchangeably. They describe the exact same physical transition, a liquid becoming a solid. We just use specific vocabulary to track this energy transfer across different materials, whether we are freezing an ice cube or watching a puddle of liquid candle wax solidify on a table. We can harness this physics to solve a practical problem, using heat to make things cold. Long before electric refrigerators, people developed the matka, or earthen clay pot, to chill drinking water in the blistering heat. Water seeps through the porous clay wall. To evaporate, these molecules need latent heat, stealing thermal energy from the water inside to drop its temperature. Your body uses this exact mechanism. Sweat evaporating off your skin pulls thermal energy away, cooling you. Evaporation acts as a built-in refrigeration system, a critical tool we use to preserve our food and protect our bodies from overheating. When you scale these phase changes up to a planetary level, you get the engine that drives Earth's entire ecosystem. This flowchart maps the water cycle, a massive interconversion engine powered by the sun. The sun's energy drives evaporation from the oceans and transpiration from plants. This sends invisible vapor high into the colder layers of the atmosphere. As the vapor rises and cools, it undergoes condensation, turning back into a liquid. These droplets cling to tiny dust particles. Once they combine and become heavy enough, they fall back to the surface as precipitation, rain, snow, or hail. These phase changes are vital, continuous energy transfers that regulate global weather patterns, constantly recycle our fresh water supply, and ultimately keep the entire planet alive.